In this lesson, we're going to continue to look at the Geiger-Marsden alpha particle scattering experiment and its implications for the model of the atom. So this is the Geiger-Marsden experiment. So what we've got here is an alpha particle source, which was radon 222 in the particular case of this experiment. And okay, so this provided the beam of alpha particles, which was fired at a very, very thin gold foil or gold leaf. And then they used a zinc sulfide screen to detect the alpha particles. So what happens is when the alpha particles hit this screen, tiny little specks of light are produced called scintillations. Now this screen could be rotated around the gold leaf sample, so they could detect whether the alpha particles were being deviated as they passed through the gold sheet or leaf. Okay, so just reminding ourselves what they expected following Thomson's plum pudding model was that this beam of alpha particles would just pass straight through the gold leaf and hit the screen there. Now the reason for this was to do with the model. Okay, just reminding ourselves what the plum pudding model said was that the atom consisted really of a whole load of positive material with negative particles dispersed evenly throughout that material, like the currants in a plum pudding cake. Okay, so the key point here is that both the positive and the negative charges are evenly distributed. There are no concentration of charges, so when these extremely high energy alpha particles are fired at this gold leaf, they will just pass through because the electrostatic interaction should be really, really weak, since the charges are so evenly distributed throughout the structure. But that's not what they saw. What they saw was this: whereas most of the alpha particles appeared to travel pretty much straight through the gold leaf with very little or no deviation, some of the particles got deviated by a certain amount, others were deviated further, and some still further. And every now and then an even more surprising result was that some of the particles were actually deflected straight back. They were quoted as reflecting their surprise to this result by comparing it to firing a bullet at a piece of tissue paper and discovering that the bullet bounced straight back. So these were quite surprising results. As a result of these results, they clearly had to abandon the plum pudding model for the atom and find a new model. And the task of finding a new model for the atom came to Ernest Rutherford, who defined what is now known as the nuclear model for the atom. Okay, so in Rutherford's nuclear model we have a nucleus which contains nearly all of the mass of the atom with a positive charge and negatively charged electrons orbiting this positively charged nucleus. Now the distances between these negative electrons and the nucleus is enormous, so there's a huge amount of space now in the atom. So we've got the positive nucleus. In the case of the gold atom, which has an atomic number of 79, that nucleus has a charge of plus 79. And the alpha particles which are being fired at it, these are helium nucleuses, so they're a lot smaller than the gold nucleuses. These have a charge of plus 2. So the results of the Geiger-Marsden experiment can now be explained in terms of this model. We see that as these positively charged alpha particles approach this huge concentration of positive charge in the nucleus, then electrostatic force will take over and cause that particle to get deviated. So what does this scattering or deviation depend on? Well, first of all, it depends on the distance between the alpha particle and the nucleus. Okay, so where you've got an alpha particle coming near to the nucleus, then you're going to get an interactive electrostatic repulsive force between this positively charged nucleus and this positively charged alpha particle, and it's going to be repelled and deviated as it comes near to that nucleus. and that accounts for that deviation. Likewise, we have an alpha particle passing here. Well, it's further away from the nucleus, so there's going to be some deviation, but not as much. So here, there's a weaker interactive force, and that results in less deviation. And then every now and then, you're going to get an alpha particle coming towards a head-on collision with this nucleus, and that repulsive electrostatic force is going to result in the alpha particle being repelled back in the opposite direction. Now, these events where there were very large deviations, or where the alpha particle was repelled back in the opposite direction, were very infrequent, and this suggested to Rutherford that this nucleus was clearly very, very small indeed compared to the size of the atom. In fact, it's of the order of 10,000 times smaller, the radius of this nucleus, to the radius of the atom. So there's a huge amount of space involved in the atom, which meant that most of the particles could get through with very little deviation, and only a few were going to be repelled completely back in the opposite direction. So the first thing that the scattering depends on is the distance from the nucleus. The next factor was the charge on the nucleus. So the smaller the charge on the nucleus, the smaller the electrostatic repulsive force, and the smaller the deviation. So, for example, if this experiment was repeated with a sheet of thin silver foil rather than gold, then we'd expect different results. Because the atomic number of silver is 47, therefore the charge on the silver nucleus is only plus 47. So you'd expect weaker interactions and smaller deviations upon the approaching alpha particles. And the third factor which affects the deviations is the speed of the alpha particles. So the more time they spend near this nucleus, then the greater is the deviation. That's to say, a longer time near the nucleus gives more time for the electrostatic force to act on the alpha particle, and therefore produces a greater deviation. So the slower the speed, the longer the interaction acts, and the greater the deviation. And likewise, the faster the speed of the alpha particle, the less time the force has to act on it, and therefore the smaller the deviation. So higher speed, smaller deviation.